Okay, good morning, everyone. So today we have one of our own, Onur Keleş, who is a KUIS AI Center Fellow and a PhD student at Multimedia Vision and Graphics Laboratory. And today he will talk about self-organized operational neural networks with applications in image super resolution. So you can start, Onur. Thank you.
Thank you, Aykut Hocam. Hello, everyone. My name is Onur Keleş. I am an electrical and electronics engineering student doing my PhD with Professor Tekal. Today, I am going to talk about the recent concept, self-organized operational neural networks and their usage in super resolution tasks. So this is the outline of the talk. First, I will have a brief introduction. Then I will talk about operational neural networks. After that, I will introduce their self-organized variants. Later, we will look at the usage of self-organized operational neural networks in the super resolution task. And finally, I will conclude this talk. So the neural networks dominate the computer-related tasks today, actually. The reason lie under that is the universal approximation theorem. It states that any nonlinear function f can be approximated as function g by a multi-layer network with the desired accuracy epsilon given enough hidden units. So this theorem is strong, but it's just an existence theorem. By looking at the theorem, we cannot say something about the necessary architecture to perform a task or hidden units, layers, and neurons. That's why we have many models and different approaches to any given task, for any given task, actually. So we know what's a neuron. It's the computational neuron is inspired from the biological neuron. As you see, biological neuron has dendrites, from which it receives the electrical signals from other cells. Then it collects it in its cell body or soma, processes it, and then if the neuron is fired, it transmits the electrical signal through its axon. And today's computational neuron is similar to that. The current neuron model is proposed in 1943. It collects the information from its other nodes with some weights, and it multiplies the inputs with weights. Then it collects, accumulates, or pools the signals in its soma, let's say, with some bias. And then if it's activated, then it is processed by an activation function. And then if it is activated, it is transmitted to other neurons, actually. But this neuron model has, our aim is to find a nonlinear function, right? But operation in nodes is multiplication, which is linear. Operation in soma is summation, which is also linear. And operation in axon, let me say, for instance, ReLU, today it's very popular. So if we look at something nonlinear, why is the only nonlinearity in the model the activation function? What if we also make the operations in dendrites and soma nonlinear? What if we add more diversity to the neuron? So this idea brings the generalized operational perceptron model. As you can see here, the weights are no longer just multiplied, but this new, let me say, processing model is some function of weight and the input. And then, as you can see, it is no more just summation. It can be anything. I will explain what I mean by anything. And then still we have the activation function. So the main idea is to make the neuron as nonlinear as possible by changing those operations also to nonlinear operations. What are those? As you remember, I named dendrites, not actually the references here, named the dendrites as nodes. then the summation operation is pooling, actually accumulating the signal. In terms of pooling means that actually, and we have activation table. So nodal operators can be any operator. For instance, it can be an exponential operator. You should, I don't know, can you see from the table? Is it clear? Or is it small?
Oh, it's okay.
Maybe I can zoom a little bit. So nodal operators, as you can see, can be any operator, exponential or some second or third order polynomials or sines. Actually, any deterministic function that you can differentiate. Then the pooling, we are used to use summation, but it can be, for instance, correlation, or we can look at the maximum or the median of the, the signals, incoming signals. And activation function, we are used to, ReLU or ELU or soft plus or any nonlinear function. So the aim is to make the neuron as nonlinear as possible. So a neural network whose neurons are generalized operational perceptron is called.
Why is that critical? I mean, Onur, I don't get it. Why is it so critical to make it nonlinear? I mean, I know you from the beginning, that's your target, but I don't understand why is that critical?
I mean, we are mostly performing.
Because the whole thing, I mean, the reason I'm asking, whole thing at the end is a nonlinear thing, right? Like.
Yes,
Yeah.
but
So why is that? Yeah.
But we are using only one nonlinearity, and it's only the activation function. Actually, by improving the nonlinearity in everywhere in the neuron, we can maybe perform the task faster or better, let me say, in terms of accuracy or, desired performance, let me say. So that's why we are trying to do everything as much nonlinear as possible, let me say. This is the idea behind the ONNs, operational neural networks, and their self-variants, actually.
Excuse me, can I ask a question?
Yes, of course.
So whenever you increase the nonlinearity of your model too much, then you're increasing the complexity. So
exactly.
wouldn't be the increasing of, wouldn't be the chance of increasing the chance of overfitting? I mean, you overfit your model and you decrease the generalization.
I mean, if we have enough data or our model is not too small, then probably we won't overfit, but we will do that task better. I mean.
So with increasing the nonlinearity,
yes,
you are not avoiding overfitting.
I mean, how can I overfit? I mean, in this current neuron model also we can overfit. But what are we doing for not overfitting? Either we use more data or we use maybe bigger models. So we can do the same thing for here.
Okay, I see. Thank you.
You're welcome. And note that when the nodal operator is multiplication and the pooling operator is summation, then we have the current neuron model actually. So building an ONN is a really how to say, it's troublesome to build an ONN. It's troublesome. The fastest way is actually synaptic plasticity monitoring. I will briefly explain it. Synaptic plasticity theory says that learning is the change in the connection strength between neurons. Whenever we learn something in our brains as human beings, the connection strength changed. And the bigger the change, the more the learning actually. So this theory says that if we look at the variances of the weights during the learning, then we can decide on which operator set is the best for the current task actually. So what we do, assign random sets to each neuron. Then we train our model for a small number of steps, say 20 epochs or maybe 1,000 iteration, that much small. So, and then we monitor the variance of the weights in each operator set in each layer. But this is for one run. I mean, maybe our model is not too big to assign every, operator set in our library. So we need to do several runs. I mean, maybe 40 runs. After 40 runs, we monitor the variances in each run, and we look at the variances, and we choose some number of operator sets, maybe 10 of them is enough, with the highest weight variances or highest health factors. The variances are called health factors. After determining those operator sets, then we start to randomly assign them to neurons according to their variances. And we do, again, some small trainings. I mean, again, maybe 10 epochs or, I don't know, 500 iterations maybe. And again, following their health factors, we can assign operator sets proportional to their variance. So this is the idea of operational neural networks and the way to build them. But if we move to the operational neural networks and look at the motivation behind it, we already see that it's troublesome to obtain a operational neural network. I mean, you first have to find the optimum operator sets, and it takes even some time as smaller trainings for some epochs. And then ONN needs unbearable long time to train. Why? Because we are using expensive functions like exponential, sine, or chirp, whatever. And each task needs its own structure. I mean, an optimum set for one task may not be optimum for others. And even for the same task, if we change the model, I mean, if we add one layer maybe to between, then we need to do this operator search again, because the model changes and the operator set that we found as optimum is for that current model. If we insert a layer, then we have to refine actually the operator sets. So our whole aim is to approximate the desired function. Remember the universal approximation theorem. We try to approximate the desired function with some combination of deterministic functions. But what if it cannot be built with them? So how else can we approximate a function? Do we know any method? And yes, we can use Taylor series expansion. We know the Taylor series expansion, right? If it is infinitely many times differentiable at point A, then its Taylor series expansion around the point A is given with this equation. So let's truncate it at Q orders, at order Q, and rewrite the terms. Actually, just name those coefficients as W. But actually, we can learn these coefficients, right? For this approximation, let me say, approximation of the desired function f, for this approximation, if we give it an input tensor, the parameters can denote the Q banks of convolutional kernels, I mean W1, W2, up to until W sub Q. And the W0 is biased. Why? Because it's just a constant term, actually, as you can see here. Also, we know that Taylor series expansion is, how to say, it is a good approximation around the point A. But if we go further from the point A, the approximation is no more good, actually. And it's getting worse and worse if we go far from the point A. So we need to bound our input X to the close to the point A. For instance, if we choose as our this point A as half 0.5, then we can use an activation function as sigmoid, because we know the sigmoid, the range of sigmoid is 0 and 1. And if we using A equals to 0, then we know that tangent hyperbolic limits the output, actually everything, every linear thing, to -1 to +1. And this is the illustration of a generative neuron. This neuron is called generative neuron because it tries to approximate a function by the idea of Taylor series expansion. As you can see, for instance, let us say the Q is equal to 3 in here. If Q is equal to 3, then what we have? It's first order, second order, and third order. So we have W1, W2, and W3. And as you can see, we convolve with these kernels some powers of the input tensor. This is the first power, the second power, and third power. Then we sum them and we add the bias term. And with some activation function. Why is it necessary? Because we need to limit the output so that we can use the output for the next layer or for the next generative neuron. And that's the idea behind the self-organized operational neural networks. And why it's self-organized? Because we are still using some operators. Remember that in ONNs, we call them nodal operator, pooling operator, and activation operator. It finds the necessary operators itself. So that's why it is called self-organized operational neural networks. We don't need for any function search, as in the ONN case. It is more flexible because it can find the element-wise necessary operators. I mean, we don't have any limit for this weight, for instance, and it does not have to be related with this weight, actually. It can learn the its operator itself. And it has the potential to be applied in parallel. Normally, those inputs and those weights are stacked, and then the convolution operation is performed, but it has the potential to be applied parallel. So if it can be parallelized, then the required time for the training is just same as the ConNet for the same configuration, let me say, as Q equals to 1. The only caveat is here is the memory requirement. As you increase Q, you increase your memory requirement. And for Q is equal to 1, we have exactly the common neuron model that we use today. I finished explaining the self-ONN. I mean, what is a self-ONN? Then let's have a look at their application in image super resolution. What is super resolution? We have a degraded image, and we try to restore that image. As you can see, we have a downsampling matrix, the reducing the resolution. We have the blur kernel. Why? Because when we apply downsampling, we don't want any aliasing, and we have the inevitable noise, actually. So image degradation is, degrading the image, and super resolution task is to reconstruct the original image. Nowadays we have popular super resolution models like EDSR. EDSR is mainly consecutive residual blocks with pixel shuffler for upsampling. And we have VDSR. It's actually modified EDSR. It's just wide activation, actually. In residual blocks, it increases the resolution, passes it through nonlinearity, and again, later decreases the resolution in the residual block. And we have Arcane Model. It uses residual in residual. I mean, you concatenate 3 residual blocks and 1 big skip connection. That's residual in residual. And it also uses attention blocks. And we have some GAN-based methods like SR GAN, ESR GAN. And in this work, we choose to apply the self-ONN approach in EDSR because as you can see, it's consecutive residual blocks and VDSR is derived from them. Residual in residual is not the same, but again, uses the nearly same idea except for the attention module. And it is simpler to employ EDSR idea. So we choose the EDSR actually here. And our experiments here. As the baseline architecture, we use this architecture actually. First, we have convolution. Then we have 16 residual blocks with some big, a big skip connection. And at the end, we have the upsampler part, actually. The baseline architecture uses 16 residual blocks, 3 by 3 kernels, the pixel shuffler as upsampler, and every convolutional layer has 64 channels except of course the output layer. So if we want to use the residual block architecture, we need to introduce the self-organized residual block actually. This residual block is the proposed residual block and actually the used residual block in EDSR architecture. As you can see, the input goes to 2 different directions. In one direction, it passes through convolutional layer, a ReLU activation, and again a convolution. Then they are added in here. Actually, we have an addition block, and then the output continues its way. And in our work, we proposed the self-organized residual block. We abbreviated it as SOR block. And as you can see, different from that, we have an activation block, activation function block here. Why? Because this input, remember the Taylor series expansion around the point A. We need to be sure that this X is also bounded. So if we don't put anything here, we cannot guarantee that X is bounded and its effect may propagate. So it makes the model actually unstable. So we have to add these blocks here. So to do our experiments, we need to determine our architectures. First, we want to use the pure self-ONN architecture. What I mean by pure, everything is built with generative neurons, actually, not the regular convolutional layer, but or regular neuron, but with generative neuron. So how many SOR blocks should we use in the self-ONN? It should be definitely the less than, because we believe that the less number of residual SOR blocks, less number of SOR blocks is enough to catch the performance of EDSR. So should we use 4 or 8 SOR blocks? And what if the number of channels? Should we decrease to 32 or should we keep it as 64? We run some experiments and these are the results. as we can see, as we increase the number of SOR blocks, we have some 0.2 dB gains. And when we increase the number of channels from 32 to 64, we have around 0.3 dB gains. So the decided architecture is this. SOL means self-ONN layer, self-ONN, self-organized operational neural network layer, so abbreviated as SOL. We are using 8 SOR blocks, nearly the same architecture actually, and everything here is also self-ONN layer, and we just have 8 SOR blocks here. And from these experiments, we conclude that even the 8 blocks is enough to compete with the EDSR architecture. It's baseline actually. And in our architecture, we decided on 3x3 kernels, 8 SOR blocks with 64 neurons, and it is built for Q is equal to 3. So we have the self-ONN architecture in our pocket, but what if we also build a hybrid architecture? I mean, we use both the regular residual blocks and SOR blocks, and we decided to change 4 residual blocks to SOR blocks. But which 4 is better to change actually? The first 4, the last 4? And also, should we also change the upsampler part? This part is, this part is upsampler part. So should we change the upsampler part also to their self-ONN variants? Was it this one? Yeah. So again, we run for some experiments for it, and we see that the first changing the last 4 residual blocks to SOR blocks increases the performance actually. Compare this column and this column. The difference is around 0.1 dB, less than 0.1 dB, but close to 0.1 dB. Also, we see that if we change the upsampler part also to their self-ONN variants, then we again have some performance gain. So our architecture is like that. We start with regular convolution and continue with regular residual blocks. There are 12 residual blocks, and the last 4 residual blocks and the upsampler part are changed to their self-ONN variants. These are SOR blocks, and these will be SOLs, self-ONN layers, and the convolution operations in pixel shuffler is also self-ONN layer. So we have the hybrid architecture also. We changed the last 4 part and the upsampler part. And these are the training details of for the all models. We use bicubic blur for ×2 and ×4 scales. ×4 scales are trained in 2 alternative ways. One, we start to train the ×4 scale from scratch. And the other method is we use ×2 model, the corresponding model, as the backbone. So we have the pre-trained model, we add some blocks, and then we fine-tune the block, fine-tune the backbone plus the last part, the last additional part. We use the 2K dataset as EDSR used. Actually, these settings are pretty similar as the EDSR architecture. They also use the 2K dataset, and there are 800 training images and 100 validation images. They do not make the test sets open to the public, so these validation images are used as test images. Our input normalization is the same as the EDSR paper used. We first normalized to the range 0, 1, and then we subtract the RGB mean. What do I mean by RGB mean? We find the data set mean in RGB. For our channel, we have some mean. For green channel, we have some mean. For blue channel, we have some other mean. We trained the models for 300,000 iterations. Batch size is 16 with 48 by 48 patches. As data augmentation, we use random crops from the images and we applied random rotations. We use Adam optimizer. The only difference comes in learning rate. The EDSR architecture in original paper, they used 10 to the minus 4 as their learning rate, and they halved it after 200,000 iterations. In self-ONN and hybrid architectures, our learning rate is 1.5 times 10 to the minus 4, and we halved it after each 100,000 iterations, and every self-ONN layer has QH3 setup. So let's come to the results. And these are the quantitative results that we have. The original EDSR paper reported the PSNR and SSIM, and also we include the recent perceptual metric, it's LPIT. This metric is perceptual metric, and we report here, I don't know if you use LPIPs. LPIPs have several models. We used here AlexNet LPIPs, let me say. And these arrows indicate that whether this metric, when this metric is higher or lower, the performance is better, actually. So EDSR baseline has these results, actually, PSNR and SSIM. In the original paper also, PSNR values are really close. By the way, these results are reproduced. They are not taken from the original EDSR work. They are found by retraining the models. The SSIM calculation is different from the original EDSR paper, I believe, because they did not reveal their, calculation, SSIM calculation. But here we use the consistent, we use the same SSIM calculation. So as you can see, self-ONN, actually pure self-ONN, beats the EDSR in actually all scales, all trainings, and in all metrics, as you can see. The performance increases around 0.06 dB, and it is just, by the way, we are just trying to, we're just trying to beat the baseline. EDSR also has some model with 43 million parameters and bigger residual blocks, more residual blocks and wider blocks, actually. So we just compete with the baseline architecture, but as you can see here, we can build it with the same setup that EDSR used. We can beat the EDSR architecture. Also, in hybrid architecture, the gain is more. It is a clear 0.1 dB gain in ×2 scales, and it is close to 0.1 dB also for ×4 scale, as you can see. So both proposed architectures outperform the baseline architecture in all metrics, and the performance gap can be as much as 0.1 dB. These are the quantitative results, and these are the qualitative results. These images are from the Div2K validation set. as you can see, the wings of the bird, EDSR architecture gives these stripes as, how to say, wavy or flickering stripes, but hybrid architecture, as you can see, does not produce such results actually here. And this is the ground truth. And also the self-ONN architecture, as you can see here, clearly, let me say, draws the lines of the rules. But in EDSR architecture, it confuses with the, I don't know with why. I mean, why does it produce such parallel lines that are not actually the texture of the roof? But as you can see, self-ONN layer, self-ONN architecture correctly produces those lines. So to conclude my talk, actually it was shorter than I expected. I rehearsed. Self-ONNs achieve the ultimate level of network heterogeneity. What we mean by heterogeneity in today's common neural models, we just use convolutions and it just use multiplication. By doing that, we let the model learn the necessary kernel transformation by itself. So it tries to approximate a function, and that function may not be the multiplication. And if it is multiplication, if the optimum operation is multiplication, then it will learn itself that, okay, we just ignore the rest of the powers, q is equal to 2, 3, whatever, and we should focus on just q is equal to 1. It can learn itself. That is what I mean by heterogeneity. It can learn the necessary transformation, and if it is not the multiplication, it will learn it. Also, in our experiments, we find that it is better to use higher order layers towards the end of the architecture. Remember that we made experiments to determine whether to change the first 4 or last 4 residual blocks to SOR blocks, and we find that the last 4 yields the better results. That indicates to use self-ONN layers towards the end of the architecture is better. That means better interpretation of the features is more important in the last layers. And in experiments also, we find out that both proposed architectures exceed the performance of the baseline architecture that we take as baseline. And a self-ONN with 8 self-organized residual blocks beats the 16 residual block EDSR architecture. And thus, as the future work, the advantages of self-ONN can be used in other applications also. And these are my references.
Thank you, Onur, for this really interesting talk. So let me turn first to the audience. So any questions? You can just unmute yourself and ask your question directly.
Onur, I should ask a question to you first, probably to start everything going.
Okay.
Show those comparative pictures, please. Can you go back to the pictures? Yes, this one. Now, the self-ONN in the middle, is that the hybrid one or the 8 SOR?
It is 8 SOR. It's self-ONN. It's not hybrid.
Okay, I wonder if the hybrid one gets the right lines correctly or not. Did you check that?
I checked, and as I remember, I think it's yeah, it's again better than EDSR, but I cannot remember.
No, it's interesting. Let's check that because
Okay.
I think if this is something related to EDSR or the self-ONN with only 4 layers can correct that? Because it's interesting, basically, these orientation of the lines are kind of screwed up in the EDSR.
Okay, I took my note.
Okay, that's it from me.
Okay, Onur, I can ask you a question. So can you go back to the training details section? Yeah. Oh no, not this one. The training algorithm. Sorry, for operational neural networks.
Oh, this one, I think.
Yeah, this one. So here, do you start with a set of functions and then you eliminate them during training, or did I understand? Yeah.
Okay, let me say it this way. We assign some index numbers. For instance, with an operator set with multiplication as nodal operator, summation as pooling operator, and activation is 0. Then multiplication, summation, tangent, hyperbolic is 1, and it goes like that. And in start, actually for this part, we assign every operator sets to every neurons randomly, actually. Their number is random. I mean, the operator set with index 0 maybe, I don't know, 10 times. And for the first run, the operator set with index 1, maybe we don't see it at all. But for the second run, I mean, to somehow guarantee that we have checked every operator set, we need to run this part several times, actually. The first 3 steps several times. After doing that, we say that, okay, we'll check every operator set. And also we are looking their health factors. The health factor is the change in the variance, actually, in the weights. And after that, we say, okay, I need maybe 10 of them or 5 of them. It's up to you, actually. I am taking only 10 of them, and I will use, and we say I will use them, but I don't know the number of operator sets that I should use. So I start to assign those 10 operator sets. After this first 3 steps, actually, I eliminate the rest. I only choose the first 10 maybe. And after that, I randomly assign those 10 operator sets to neurons. And again, for instance, I run once this training and I again check their variances. And in the second run, I assign them to the neurons such that their numbers is proportional to their health factors. And then I again run. And after that, I again check the variances and I again run. And I redistribute them according to their health factors. So it's up to me. I think maybe I said 5 runs is enough. And after 5 runs, I have a self-ONN layer with these 10 operator sets.
Okay. So I asked this simply because there is this literature on pruning deep neural networks. So this somehow resembles some of these strategies. Maybe it might be better to look at those papers. Maybe you can just
Well, I should say that the idea of ONN, the operational neural network, is Serkan Kranya's idea. He is at Qatar University, and he also collaborates with Monsef Gabush at Tampere. So the operational neural network idea is their idea. What we added here is the residual block architecture. The SOR block is our idea. So, I mean, basically, if you cascade a couple of these self-ONN layers, because of the Tanash nonlinearity there, you run into this disappearing gradients problem. And in their work, Serkan and Monsef actually use only like 2 or 3 self-organizing layers. So they don't really see that problem that much. But when we put 8 of them to compete with the EDSR deep network, we see that the performance drops. So adding this residual connections and the SOR blocks gives us the better result, basically.
Okay. Thank you, Murat Hocam. And another way to generalize this might be to include some recurrent connections. Maybe that might be also interesting to check.
To include where?
Like, for example, some feedback loops to earlier layers, like a RNN-like structure.
I see.
So that might also be interesting. And one final comment about your experimental setting. So as far as I understand here, you are introducing some additional complexity to the baseline architecture, right?
Yes.
So in that sense, I think it might be also important to report the flops, floating point operations, compared to the baseline. Did you also check that, or?
No, I didn't check the number of flops, let me say.
Mm-hmm. So if I were a reviewer that review your work, I think the only criticism I can make is this.
Okay, thank you.
Oh, Onur, I have I could have done. Were you done?
Yeah, you can continue.
Okay. So it was actually very interesting. I haven't seen this work, the ONN approach before. Well, the idea of, let's say, generalizing the CNN, and especially like in terms of like nonlinearity to increase the capacity is out there. But I'm wondering like how this can be linked back to the scattering theory of operators approach. Like in the CNN case, we can link it back to like how this can improve our learning based on some scattering theory approaches, so that we can preserve invariances and at the same time we can be geometrically stable to some sort of perturbations. But now if you just lose this linearity in CNN, how you can link it to some sort of understanding the learning? Do you have any idea or any like prior work that can be used to explain this new way of, let's say, generative neuron? That was the term I guess you used.
Yes, it's the term that Murat Hoca talked about, Serkan Hoca's term, generative neuron. And so I didn't check, I mean, scattering theory approach for convolutional networks, I didn't check it. And I don't think also that they have the, what I mean, they is the owner of this idea, let me say. They don't also check or do any work on scattering theory about self-evidence or generative neurons.
Like the very basic idea is actually simple, saying that if you want to preserve invariances, then you are kind of sort of limited to affine operators, like linear operators, but then you are limited in terms of learning capacity. So that's why we need the non-linearity part, as you initially motivated the talk. But then if you just only focus on preserving invariances, you are limited by some simple group operations, like invariance to like shifting, rotation, and things like this. And this just boils down to like simplified tools that we know in our conventional models. But if you simply take it to like CNNs with some additive nonlinearities such as ReLU, then we can suddenly become stable, geometrically stable to perturbations. That is, although it is not invariant anymore, it is still stable, that we can show through the scattering theory, as I said before. But now with this technique, if you just simply introduce like nonlinearity to the CNN, and then it becomes like a generative neuron type of, let's say, a non-linear convolutional operator, I guess, that is always learned in the back. do you see any connection, like how this can be, like, is this like stable to some, because the additional lines over there in one of the visual results you showed, do you see such patterns like jumping in so that it may or may not be stable to some sort of basic perturbations?
Onur, can you show the generative neuron slide? Yes, this one. Yeah, I mean, we have basically inputs. There are still convolutional kernels here, but the inputs are not just the images itself, but the squares and the third powers and maybe the larger powers of the input images too. So that's the idea of the generative neuron. And this basically says that this whole thing here approximates a nonlinear function better, basically. So about the invariances, I mean, it may be important in object detection and so forth, but do we really care about the invariances for inverse problems? I'm not sure. I mean, that's a good question, but I don't know the answer.
Yeah, definitely. That's like, there is a trade-off, and we know that like only focusing on the invariances is not the full answer to this, but it should also become like stable to, let's say, geometrically stable to sort of deformations. So how this approach will help basically within this trade-off? That's why that was kind of my question. But maybe it is still an open area, and it would be really interesting to check the scattering operators approach on this work, so that maybe we can extend the like understanding the internal dynamics of the generative neuron model.
But I mean, let's say if there are geometric deformations, I presume you're saying in the input images, basically, can't this basically network learn that? I mean, we are basically trying to undo whatever the degradation is, and this is blind. So basically, if the same type of degradation or deformation appears in all the input images, then this network will learn how to undo that. So this is only an inverse, basically, system that we are designing here. So are you claiming we cannot learn geometric deformations in the input images with this architecture? I'm not sure.
I know my hypothesis is that it should either focus on the invariance part more, or like the geometrical stability part. But I don't right away infer which side this new model is close to. For sure, it will have some improvement, but I don't know right away which part it is exactly.
Okay, I don't know the answer to your question, but basically, I mean, what I'm saying is, whatever the deformation function is, this network is trying to undo that deformation. So it's learning the inverse function. Whatever the deformation is, it's just learning the inverse of the deformation. And as long as it's the same deformation in all the images, it should learn it, I think. I mean, that's my guess, but I don't know the answer exactly.
And choosing Q equal to like 3, like up to third level of expansion, was
Yes.
that like empirically fine, or how did you fix that?
No, we just
It's a trade-off between the number of parameters and the power. Actually, if you go to up to 5th power, you get slightly better results, but then the number of parameters in the network increases. So it's a trade-off between performance and the number of parameters.
Okay, thank you.
And also, I mean, yeah, I mean, this has more parameters than the standard convolutional network. The number of parameters is basically proportional to the power of the you use, basically the Q you use here. But also this architecture suggests that these different convolutions can be done in parallel. So in terms of computation time, it really doesn't mean it takes longer. It has more parameters, but since we have GPUs, we can do these convolutions on different powers in parallel. So it doesn't increase the computation time that much.
So maybe we can take one final question.
All right.
Anyone? Okay, then I think we are done for today. Again, Onur, thank you for joining us today and this
I
really
thank you.
interesting work.
I thank you for attending and listening and all your for all your questions actually.
Okay, okay. Okay, then see you next week, everyone.